Okay, going over, this Michael's here. Lindsay, not here? Okay, I think we're all here. Okay, we are totally talking about Faraday's law of induction now. There's Lindsay. I actually say that so if there's ever a question, I can come back and listen to the recording and say, yes, she came right at the beginning in case I didn't mark it down. In case you wonder why I say things like that. Okay, Faraday's law of induction. In 1832 or something like that, Faraday came up with a law to explain about this motional EMF. Remember last class period we talked about motional EMF. If I have a rod moving in the presence of a magnetic field, it will create an electric field. And we learned that electric field is going to be V cross B and then dotted to the length. So this is, we call it a triple product, I believe. Cross product and then a dot product. But this is the voltage that will be produced. Excuse me, I said electric field. That's the voltage. You do the electric field dotted to the length to get the voltage. Voltage that will be produced if I have a rod going through a magnetic field. The last thing I said as we ended the last lecture was, so this, means the airplanes with a large wingspan going through the Earth's magnetic field will actually generate a reasonable sized voltage difference from one end of one wing to the end of the other wing. Now, I couldn't find a homework problem that was like that, so instead I put in one that has you calculate the force due to the charge of the airplane moving through the Earth's magnetic field. It was just as close as I could get to that, even though it's a completely different problem. Since you're producing a voltage, you can treat that like a battery or like a cell, that you have an EMF that's produced by the moving rod. And so in this situation, a resistor has been connected, and you could power that resistor, make current go through that resistor, and you just use Ohm's law in conjunction with the induced EMF to find what the current's going to be. Now, what Faraday did is he found an equation to help us do this in a simpler fashion, to help us see how having a change in what turns out to be the magnetic flux produces an EMF. So I should have information about Faraday. Nope, I don't. Did I ask you this question last class period? Okay. There we go. Now you can answer. Where does the electric energy come from in the problem of having the little slider moving in a magnetic field that creates current going through the resistor? Okay, everybody's answered. 1, 9, 2, 6. That first one, I think most people recognize that's a joke. But, I know one person answered that. I'm assuming that person was joking as well. But there are people in this world who are very certain that there is such a thing as free energy. And the fact is, it's hard for me to even contemplate that because all my life I've been taught that there isn't. And we have pretty good physics reasons to believe there isn't, but nothing in science is ever settled, right? The debate just never is settled. And so it still is not a waste of your time to look for the free energy. It's just you have to understand that it's a long shot. And so that was not the answer here. This has been very carefully studied, and it's not free energy. So moving to the others. Energy stored in the magnetic field. I will pose this to you in a way that I think will make it clear. If my energy stored in the magnetic field decreases, what's going to happen to the strength of that magnetic field? It's going to decrease. So if I have a bar magnet sitting on the desk, and I take a metal bar and swing it over and use that metal bar swinging over to light a light bulb, I clearly dissipated energy in the light bulb. If it came from the magnet, if it came from energy stored in the magnet, then what physically happened to the magnet when I did that? It had to become less magnetic. That's not what happens. The magnet will retain its magnetism because the magnetism is based on those domains being lined up, and you didn't realign the domains by swinging it over. So that one was incorrect. That was the one that had our majority of answers. So now we're left with two more. Energy stored in the resistor or work done to move the rod? Well, resistors don't store energy, friends. Resistors just take energy away and release it generally as heat. So what we're left with is you have to make that rod move. That rod's not going to move by itself. If you push the rod to make it start, as it produces the electrical energy, it's going to slow down. That's where the energy is coming from. Producing the energy is going to make it slow down, lose its kinetic energy if you just push it. And if you're continuing to hold it, you go like this, and you actually have to supply a force. So it came from the work making it move. I was telling somebody after class earlier this week about a situation that happened in San Francisco when I was teaching at PUC, where they were working on the BART train system, the Bay Area Rapid Transit, and so they turned off the power and they put big grounding rods between the rails, or well, between the power, so that no one would get electrocuted while they're working on the system. And they had like 13 of these. When they were done, they took the rods out. They had their little check sheet, and check, check, check. They're all gone. And they turned the power on, and the power in the city all went off. I happened to be in the city when this happened, and we're wondering, like, what's going on? And as I said to the person earlier, driving in San Francisco is not your happy thing to do. It's kind of a zoo. And when there's no electric lights to control traffic, it's less fun. So why did it happen? It turned out that while there were, I think it was 13 grounding rods, around half of them had been left in place. People just checked off saying they were gone when they were still there. And so when they turned on the power, they had a direct short between their high energy output and ground. And that meant that you had a huge amount of energy dissipated through those big metal rods. Well, where's the energy come from? It comes from a rod moving through a magnetic field. That's how electric generators work. And so all of a sudden it's trying to take a huge amount of energy, which means that you have to supply a huge amount of force to make that rod keep moving. And so these big, I think they're like 1.5 foot diameter camshafts, one of those got sheared, a steel shaft like 1.5 feet or something like that in diameter, was sheared because the torque that was necessary to keep it going was so large it couldn't withstand the torque. It takes a lot of energy to make those things go, especially if you try to draw a direct short from the power supply. Okay, now we still haven't gotten to actually Ampere's law, but this is, I think, is the last slide before, and then after we talk about Ampere's law, I'll come back to this slide again. If I have this square made with conductive wires, on the left that square is moving through no magnetic field. Are there any pieces of that square that are going to have an induced voltage? Excuse me. Induced voltage if it's traveling through no magnetic field? No. So you're going to have no current in that case. Now in position B, you now have that same loop, but now this side is in a magnetic, okay, change color. This side is in a magnetic field, but the other side is not. Is there going to be an induced voltage on any sides of that one? Yes. Yes, there will. There will be, and in fact, we can determine the direction even if we forgot everything that was from Wednesday by using the right-hand rule. the mythical positive charge is traveling, as you look there, to your right. And so the force is equal to, I'll write it down here. So I said the mythical positive charge because then we don't have to worry about reversing the direction. So I have V cross B. How do I use my right hand with V cross B? Index finger goes in the direction of the first item in the cross product, which was V. So I point my index finger to your right. And then I need to orient my hand so what happens next? Okay, middle finger points to the direction of B, the second item, so I rotate it like this, and my thumb is pointing up. So that means my mythical positive charge is going to go up. If positive charge goes up, what does that tell you about current direction? Now, current is the direction of positive charge flow. So that means that here we're going to have a current that goes like that. What about on this part of the wire? There's still going to be a force in the charge that's going up, but that's not going to create a current because it can't go up. But I have this current that's going to continue going through the wire because I have one part of the wire that's making a current. Now I go to position 3. Am I going to make a current there? Chad says no, with conviction. Almost. Why were you almost convinced?
It just seems like one side's going to produce current going one way and the other the opposite.
That's right. They're both going to try to make currents going up because they both have the same V and the same B. And so the net result is no current formed. Yes?
Will we still have a voltage difference there that's created?
We would have a voltage difference between the top of the loop and the bottom of the loop. Yes. But no current flow. Good observation. Okay, so we have no current here. Position 4. Now what's going to happen? Now it's going to go the opposite direction because this side is making a current go that way and nothing else is creating a current. And finally, position 5, we've gotten back to position 1, nothing going on. So here, using the things we learned about motional EMF, we can see something going on. Now, Faraday looks at something like this and he says, let me count the number of X's in the box. If the number of X's increase, then I'm going to have a current that flows counterclockwise. If the number of X's decreases, I'm going to have a current that flows clockwise. That is in essence what Faraday's law is. Now when I say the number of X's, what is that telling you? Okay, the strength of the field that goes through the loop. And of course the X's were the ones that were going through one direction. If they had been circles with dots, it would have been the other direction. It would have reversed the direction of the magnetic field. Lenz's law is the one that tells us direction. So what did we call when we talked about the amount of electric field going through a surface? What did we call that? Electric flux. So since this is the amount of magnetic field going through the surface, what should we call it? The magnetic flux. Now, you may have noticed the first slide. I had a picture here. Come on, picture. For calculating that magnetic flux. Because Faraday's law of induction has to do with the magnetic flux. So the magnetic flux, just like the electric flux, is the strength of the magnetic field that is normal to our surface. Remember, normal is just the three-dimensional equivalent of the two-dimensional perpendicular. So we take the angle theta is the angle between the surface normal, or the area vector, because the area vector is defined to be in the direction of the surface normal, and the magnetic field. So we take the angle between the surface normal and the magnetic field, and then the flux, magnetic flux, is equal to be a cosine of the angle between the two, or, doing it without writing cosine, B dot A. And that's just like the electric flux. Just wanted to make sure we go through it again rather than saying, you know this, and move on. I think I went one too many slides. We'll see. Yep, one too many slides. Oh, no, it was the right number. Okay, clicker question. I thought I had another slide before this. What had to occur for an EMF to form in a wire within a constant magnetic field? I believe this is one where you have multiple answers and hit enter. Is that, Reagan, you've answered. Is that what you had to do? Or is it just single? Okay, it's just single? Okay. Just one answer. Okay. It's a very sharply peaked normal distribution. And the 60 people are right. We had to have a wire moving perpendicular to the magnetic field. It didn't have to be a magnetized wire. It just had to be in a magnetic field and moving in a direction that wasn't parallel to the magnetic field. The charge of the wire didn't matter. As long as it's a conductor, it's going to do it. If it was not a conductor, then it wouldn't have worked, but I didn't have anything here that said about conducting or not. When you say wire, you mean a conducting material. Okay, so now I'm pretty certain, we're going to talk here about Faraday's law. This picture is showing a generator. Once again, looks just like an electric motor. You have a magnet out here on both sides. With that magnet, what direction is the magnetic field lines, are the magnetic field lines going inside the generator? They go out of which pole? They go out of north and into south. So our magnetic field lines in this are going like this. And then we're going to force that coil to rotate. And by forcing that coil to rotate, we're going to have a wire moving in the magnetic field, and that's going to create our EMF. Now, Faraday's law of induction, which, God's my witness, it better be on this slide. It's not. Okay, I'm moving past it because okay. The organization here, I did this organization on, Tuesday? And it's not what I want to do today. I want to go straight to Faraday's law of induction. Okay, I'm just going to go back here to this picture and write Faraday's law of induction. Faraday's law of induction says that the EMF is equal to, I'm going to put a minus sign here. That minus sign is a reminder. I actually use this equation only to find the magnitude. And the minus sign is a reminder that I need to also determine the direction. The change in the magnetic flux divided by the change in time. Now I have to do one more thing to modify this because that technically is the correct equation if I have a single loop. If I have two loops, how do you think it's going to change? I have to multiply it by 2. So in general, we put times n for the number of loops. So it's the rate at which the magnetic flux changes that tells us what the induced EMF is going to be. Now that's about as simple of equation as you see anymore in physics, right? Sure, when we started we had simple equations like that, but of late they've been more complicated. But that's a pretty simple equation. The induced EMF is just minus the change in flux divided by the change in time, and then if we have multiple loops, times the number of loops. the whole derivation here and going to the next pages was calculating, okay, what's the motional EMF produced on each of the 4 wires? And it turns out only 2 of them have a motional EMF induced. And then we take, okay, so one EMF is this way, one EMF is this way. They're in a loop, so they add together. And from that, you get the EMF is, well, I'll jump right down to here. The EMF is omega, the rate at which it's rotating in radians per second, times n, the number of loops, times b, magnetic field, times a, the area, times sine of omega t. Now you look at that sine of omega t. Uh-oh. What did we have for the flux? Yeah. Be a cosine of theta. Well, if theta is omega t, if I'm rotating, then I have that. And so you might say, well, how does the EMF have sine in it then? And here's the answer. Calculus. We can do this without calculus, but lots of waving your hands. But the true equation is the induced EMF is equal to, once again, that minus that reminds us of direction, the derivative of magnetic flux with respect to time. When you do the derivative of cosine omega t, derivative of cosine is minus sine of omega t times the derivative of the inside omega. And so that's going to be equal to this. So it comes out from just using that equation as well. Yeah?
What was omega again? Sorry.
Omega is the angular frequency. That is the number of radians per second. Right? So if you look there, theta, our angle theta, was equal to omega t. If you have to go back months when we talked about angle changing. So the voltage produced by a generator is produced just like this. You have the picture I showed with the coil rotating magnetic field. The maximum EMF it can produce is the number of coils times the magnetic field times the area times omega, the angular velocity. That's the maximum. But it depends on angle, if it's going to be positive or negative, and somewhere in between. And so that's where the sine omega t comes from. So if you're trying to make an electric generator, take the example, my parents, when they were out in the Philippines, they had a couple of hydroelectric generators. And so those hydroelectric generators, they have water running down, and it makes a water wheel turn, and then that turning water wheel goes to a loop that's rotating in a coil. What frequency do we use here in America for our electricity? We use 60 hertz. In the Philippines, at least where my parents were, they also use 60 hertz. I think the Philippines might use different frequencies depending on where you are, just like they use different voltages depending on where you are. And their electricians are of such a caliber that when you look at a plug, there's supposed to be different plugs for the different voltages, but not always. So, for instance, refrigerator no longer works. Anyway, they were trying to do 60 hertz. So if you're trying to do 60 hertz, you need omega to be the right frequency so that you're making 60 hertz. So for 60 hertz, remember, omega is equal to 2 pi f. So if f is equal to 60 hertz, then omega is equal to 2 pi times 60 hertz equals 120 pi radians per second. Basically, you need the water wheel to rotate 60 times a second if you want 60 hertz power. But that sets what omega is, and then your area of your loop, your magnetic field, and the number of loops needs to be the right value, so omega NBA gives you the voltage you're looking for. Now, I go through this, we'll talk more about that, but one of the interesting things were, you want to keep the same frequency, but I talked about what happened when they had the short there in San Francisco. It created a really big torque and sheared off a bolt, or not a bolt, but a big shaft. Well, when something happens like a refrigerator turns on, you have a pump that turns on, and that will initially draw a lot of current. If it draws a lot of current, where's the energy coming from in the hydroelectric generator? The energy is not coming from the pump. It's coming from the moving water. Now, their moving water was only dropping a reasonably small amount, and when you have suddenly a big change in the load, it would slow the wheel down because your water just couldn't keep up. And so the frequency would drop when the refrigerator turned on. But then it would catch back up and come back up. Then somebody else's refrigerator turns on and does the same thing. And so the clocks in something like the microwave, because in America our frequency is very well regulated, a lot of things like our microwave ovens simply use the frequency of the electric waves to determine the time. Well, since the frequency kept jumping down every time some appliance turned on, what happened to the clock in the microwave? It was always slow. You lose, I think they said they lost like an hour in a day or something like that because the frequency keeps jumping down. It was really interesting, after teaching physics for a while, going and looking at it, it's a lot more interesting to me because I've talked about all of these pieces and now I see actual practical application. It's almost like I've been there. Okay, so this gives you a sinusoidal voltage. Here's a sinusoidal voltage. Simplest question one can ever ask about the sinusoidal voltage. What is the average EMF? It's 0. Hence, we never ever talk about the average voltage for what we call an alternating current system. We call this alternating current because the voltage is going positive and negative, which means if I connected a resistor to it, the current would first go this direction, then it would go that direction. It would keep changing direction, alternating. So for an alternating current system, the average voltage should be 0, which means it's a useless thing. Yes, this is 0 average voltage. That does not mean it's safe to touch. Doesn't tell you it's unsafe either, but it doesn't help you. Doesn't tell you anything about how much energy it can produce or so on. So we don't talk about the average. Instead, we talk about the root mean squared. Now, we learned root mean squared last semester. What does root mean squared mean? It's a process, and all those words are in the process. You have one of them out of order. You take the square root of the average of the squares. So the process, the first thing you do is you square it. So if I have the sinusoidal voltage and I square it, what would the square of this look like? What is the square of 0? 0. So what is the square of omega NBA? Well, it's bigger, right? So I'm just going to go to bigger. So it goes like this. What's the square of 0? 0. Whoops, missed. What's the square of minus omega NBA?
Smaller. Oh, no, sorry.
Bigger again. It's the same as the square of omega NBA because minus 1 squared is 1. So it's going to go like this. Now, it turns out that's still a sine wave, or actually it's a minus cosine wave with an offset. The average of this is halfway between omega squared, n squared, b squared, a squared, and 0. So you do the square first, and then you take the average, which is halfway in between. Okay, so that gives us e squared. That means average. And then the final step, we squared it, we took the average. The final step is take the square root. So EMRMS is that. Well, if you look at this, square root of 1/2, 1 over square root of 2, omega squared, n squared, b squared, a squared. Well, that was just the EMF maximum squared. So you square root the EMF maximum squared and you get the Emax. So the RMS, and this works for any voltage, the RMS voltage, if it's sinusoidal, is 1 over square root 2 times the maximum voltage. Now I have to make sure you understand that's if it's sinusoidal. You could define VRMS for a DC. Here's 0, here's V. If I square that, I would get V squared. I take the average of V squared, I would have V squared. And then I square root it and I have V. Right, so the RMS value for a DC voltage is just the voltage. If I, instead of that, had something like this, a square wave that goes from plus V to minus V, that would also have an RMS value of just V. So the RMS equation that we use is only specifically for sinusoids. Cassie had an equation. Yes. What's your equation, Cassie?
I don't know. That's the problem. So is there any, are there circumstances when the up part will, like one side will have more of a spike than the other side, and then it'll like, it's not even?
Okay. Are there situations where it's not centered on 0? That's what you're saying, where you have an offset. You can make a situation with an offset, but a generator won't have an offset. The generator will be balanced around whatever you put for your ground. Now, if you change the ground to something else, well, that's how you put the offset in. So we talk about this RMS voltage when we talk about AC voltage. So the voltage that we nominally use in our buildings is 120 volts. So what we have nominally, and of course nominally means it's in name, not in reality, is we have VRMS is equal to 120 volts. If that's the case, what is Vmax? Okay, we had VRMS is equal to 1 over the square root of 2 times Vmax. So exactly like Tori said, Vmax is equal to square root of 2 times VRMS. So square root of 2 times 120 volts is equal to, tell me. I mean, it's like 169 point something.
169.7.
So when we say we have 120 volts here, it actually has a maximum voltage of 169.7 volts. And what's the minimum voltage? Negative 169.7 volts. So when we say 120 volts, we're actually talking about a sinusoid here that's varying between plus and minus essentially 170 volts. Because we often don't even stop to think about what that means. And now we have the ability to do that. Now, while I'm on this topic, we have learned that power in electric circuit is equal to IV, the current times the voltage. If I have an AC circuit, the current and voltage are constantly changing. So at one instant I might have a current of 0 and a voltage of 0. So I might have a power at that instant of 0. But an instant later, I might have a big current and a big voltage. So the power is constantly changing. So what we talk about for AC power is the power average. And to find the power average, well, we know that power, if it's a resistor, can be written as V squared over R or I squared R. And so let's take the V squared over R one. If I'm going to find the average power, I'm going to take the average of V squared divided by R. But if we go back to our definition up above, the VRMS is the square root of the average of V squared. And so if I square everything here, I would have the average of V squared is equal to VRMS squared. And so the average power used in a resistor is the RMS voltage squared divided by resistance. Part of the reason we use the RMS is because our equation for average power is just the same as our equation for power in a DC circuit. And in fact, it works out in all cases equals IRMS squared R equals VRMS IRMS. So the average power in an AC circuit, a circuit where you have fluctuating voltage such as you make with a generator, is calculated just using the RMS value for voltage and current. Now, I don't know exactly when in the textbook that was introduced. I'm pretty sure it's in the past. I have been specific in not asking you questions about anything RMS because there was really nothing that was pertinent to it until now. Not section 19.7. And this is just talking about how you make the generator. Well, you make the generator just like you would an electric motor. If you make a split armature type style of motor, that's how you make a DC motor, right? Well, if you were to do that with your generator, you'd be making a DC generator. Because with that split armature, when you come around to the part that would be making the negative voltage, you're switching your connections. And so with the split armature, you can make a DC electric generator, except for that DC electric generator would be going like this. Why does it have up loops one after the other? Because you're flipping the connections when you have the split armature. Remember the split armature, you have the two connections with the brushes. So that, this side here is the positive side, this side here is the negative side. And every time it does a half turn, you just reverse the side of the ring so it's always positive. So that's one way of making a DC generator. Now, that's DC. Is that what you get from a battery? What's different? Okay, the battery should be smooth. This is anything but smooth. Oftentimes, we don't like it to be rough like this. So we do things to try to smooth it out. So what ideas... before I go on to the smoothing, there's a way to do this without having a split commutator. That's using diodes. You use a diode bridge where you have your AC generator. This little tilde means it's AC. Do you have a question, Michael? No. Okay. You take that output and you make a bridge with diodes. And any reasonable person in this class should be saying, what the heck are those? Except for the people who've taken circuit class. This here is the symbol for what we call a diode. And diodes simply allow current to flow one direction but not the other. So when you take this, if this is positive, then that positive will go this way because the current can flow through it. If it's negative, it can't. If this side here is positive, the positive can go this way. So it turns out this side will always be the positive side. And the counter to that then is the other side is always the negative side. And so using those diodes that are just one-directional switches for electricity, you can make it so you, without having a split ring, have a DC generator. But like I said, we want it to be well-regulated. Well-regulated would be smooth. One way of making it well-regulated what I put in the center. Those are supposed to be equal length. A capacitor. You put a capacitor. That capacitor stores energy in the form of an electric field or charge separation. So what's going to happen is one side of that capacitor will be positive, one side will be negative. You charge it up, you connect something to, okay, let's say you don't connect anything to it. What's going to happen is you're just going to charge it up and it'll stay perfectly regulated. No wobble at all. But as soon as you put a load on it, it's going to start dropping down because you'll have power return from the capacitor when the voltage drops. So with this design, your voltage pattern would look like that green pattern. So it's better regulated. And I'm guessing those of you that have taken the circuits class have studied how to make a well-regulated power supply? Kind of. What you really do in real life is you get a voltage regulator chip that has things like a Zener diode in there that will cap it. You can make very well-regulated DC voltages from this. Those are the methods. So here's where I have the figure for what a rectified generator looks like. Something that is now DC. Notice DC does not mean constant. Batteries were constant. DC just means that you always have this side's positive and this side's negative. But the voltage here is clearly fluctuating. It's called rectified because it's been converted to a DC. It's been made right. You've all learned about sinister and recto, whatever, right? In chemistry. You know that left-handedness is called sinistrality, right? Yeah. Sinister, yeah. Anyway, let's not go on that. I've talked about enough things. I don't have anything to say on that one. I do have this question. Which parts are necessary for an AC generator? And this is the one, Reagan, where you have to put in two answers and then hit enter. I knew I had one. Okay, I'm still waiting for you. For my TA. There we go. All right. Woo. 5, 10, 8, 0, 11. Okay. I must have been too varying in my descriptions today, not straight enough forward, because we did not talk about electric field today except for in an analogy for electric flux versus magnetic flux. The electric field was not part of the generator. Yes, you do create an electric field in the generator. That's what's inducing the EMF. But that's not part of it. The other two answers that had big numbers, the strong magnetic field and the rotating coil, those are the two things you need to make an AC generator. What would the split commutator do? That would give you a DC generator. So the people who answered that, you weren't off in left field. You were just, that's the DC case. Now, I remember now, when I've got 4 minutes left, there was something I did not explain. It probably is in the upcoming slides, but I'm going to make sure I cover it now so we have it in 4 minutes. Faraday's law of induction. The induced EMF is equal to minus n change in magnetic flux over change in time. What things will create a change in magnetic flux? And to help you answer that, I will rewrite the equation for magnetic flux. What things would create a change in magnetic flux? Okay, change in magnetic field strength. Strength. What else? Change in angle or change in area. Any one of those three things will induce an EMF. When we talked about the motional EMF, we didn't have as many options. We just had motion. Now we have, well, if the magnetic field strength increases, it will create an EMF. If the area increases, it will create an EMF. If the angle between the two changes, it will create an EMF. So we have three things that can vary. How do we determine the direction of the induced EMF? Now, when we did the first example, remember I have position 1, position 2, position 3, position 4. We looked at each side and we were able to determine. Lenz's law is the second piece that always works in conjunction with Faraday's law. So this here is Faraday's law of induction. Why law of induction? Because you are inducing a voltage because of the change in flux. To go with Faraday's law of induction, we use Lenz's law that tells us the direction of current, and if you know the direction of current, you know which side is positive, induced. And here's how it works. Lenz's law can be written very simply. The induced magnetic field opposes change in flux. Now, the words are simple, like I said. The meaning is simple, but connecting the meaning in the words is where the trick is. So let us say that I have, this is a coil. So charge can go around the outside of the coil. And just for simplicity's sake, this is actually a magnet that has two poles, the north and the south. Let's say that these are both north and the south is down here in my hand. So if I take this magnet and I bring it closer, what happened to the magnetic field strength? It increased. So Lenz's law says the induced EMF is going to oppose the change in magnetic field. So the magnetic field, if these ends were north, the magnetic field is going this direction and getting stronger. Lenz's law says the induced magnetic field is going to oppose that. So the induced magnetic field is going to have to be pointing this direction. If the induced magnetic field is pointing this direction, how to find the direction of the current going in the loop? It's one of our 3 right-hand rules we dealt with last class period. It's something like this. You put your thumb in the direction of the magnetic field in the center, and your fingers tell you the direction the current goes. So if this was a north magnetic pole and I brought it in this way, the induced magnetic field would point this way, which means the current would have to go that direction. That's what Lenz's law tells you. Now before we forget, back it up. This is still north. I start with it here and I pull it away. What happens to the strength of the magnetic field? It decreases. So what does Lenz's law say is going to happen? It's opposing the change. So since the flux went down, what's it going to do? It's going to make a magnetic field to try to keep it the same. So it's going to make a magnetic field that points the same direction to try to keep it from changing. So then, if I pull it away, the current is going the other direction because the magnetic field induces the other direction. So that's Lenz's law. It tells you which direction is going to be positive or which direction current would flow. And on Monday, we'll have some cool demonstrations involving this. Today is Friday, right?